Welcome to the Altera online presentation VHDL Basics. By the end of the presentation, you will be able to construct complete models using VHDL. You will be able to generate general logic functions and build hierarchical designs. We will begin this course with an overview of VHDL. Next, we will discuss design units within the language. This section includes the discussion of entities, architectures, configuration, and finally packages. We will then look at the language in more detail, studying the constructs used within the language to create models. These include, for example, constants, signals, and processes. Next, we will learn how VHDL code is synthesized and look at some commonly used functions and how they're constructed. Finally, we will discuss designing hierarchically within the language. So let's start with an introduction to VHDL. VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. It is an IEEE approved standard that we use to describe models for both simulation and synthesis purposes. For some terms that we're going to use throughout this presentation, the first is HDL. HDL stands for Hardware Description Language, and it refers to using a text-based programming language to model a piece of hardware. There are two ways to do modeling with HDL, what we call behavioral modeling and structural modeling. Behavioral modeling is describing the component by means of its I/O response, whereas structural modeling is actually putting building blocks together to form a complete circuit. The term RTL, or Register Transfer Level, refers to a type of behavioral modeling. With RTL, the design is described in terms of register stages with combinatorial blocks of logic between them. Synthesis is the act of translating this text-based HDL into a circuit and then optimizing that circuit. And the process is the basic unit of execution in VHDL. Behavioral modeling specifies only the functionality of a circuit, but does not actually indicate the actual structure of the circuit. The relationship between a component's inputs and outputs is clearly defined, but only at a high level. The actual circuit implementation is left up to the interpretation of the compiler. Structural modeling, like behavioral modeling, specifies the functionality of a circuit, but it goes further and calls out specific hardware implementation, including building blocks and their connections. During RTL synthesis, code that is written is analyzed and equivalent logic structures are generated. So in the upper left, you can see a process block with a case statement inside. When coding this case statement, the logic I'm seeking is a 4-input mux. The synthesis tool, recognizing the case statement structure, performs two steps, translation and optimization. During translation, the synthesis tool will directly translate the HDL code into a gate implementation. During the optimization step, the synthesis tool then tries to improve the logic by making it smaller or faster. So, for example, to make the logic smaller, it may try to remove redundant logic. Or, to make it faster, it may try adding some parallel structures to it. Both VHDL and Verilog can be used as higher-level languages that support behavioral synthesis. Other languages like Able, Palasm, and AHDL are more structural. With those languages, you specifically instantiate the component you want in your design, such as a D flip-flop, and the tool goes into a library and drops that into your design. Very similar to low-level schematic entry of the old days. VHDL supports both methods of designing, both by inference and by instantiation, which is what makes it so powerful. By simply describing the functionality of a circuit and letting the synthesis tool build it for you, you can produce very powerful functions in just a few lines of code. Doing this using a structural language is much more like programming in low-level assembly, with the circuit having a very specific implementation. so changes to that implementation do not scale easily and require much more effort. This slide shows the flow diagrams followed by VHDL synthesis and simulation tools. Notice the tools use distinctly different flows. On the right, you can see that the simulation compiler takes your VHDL design and any VHDL libraries used to create a simulator-specific simulation model. It then executes simulation on this model. Using this model allows the simulator to perform faster simulations than if it was trying to read the code line by line while a simulation is actually running. During simulation, the tool takes any test vectors or stimulus provided by you and produces output waveforms or text files that can be used to verify proper operation. As an alternative, you can also write your simulation stimulus using generic VHDL code called a test bench. The test bench code gets compiled along with the design so that the stimulus is also in the compiled simulation model. This means you do not need to provide simulator-specific test vectors when you execute your simulation. The advantage of the test bench is that your stimulus is portable just like the design files. Notice in this flow there was not any mention of hardware or target architecture. This is because a simulator is going to execute code as it is written. In a sense, it really does not care where the design is going, as it is only concerned about interpreting the functional description provided by your VHDL code. On the left, the synthesis compiler takes the same VHDL design and libraries to produce a synthesized netlist. This netlist is your design translated into the primitives that make up the target hardware architecture. Notice that in the synthesis flow, a technology library was used. Every FPGA family has a different library that a synthesis tool uses to map a design to its specific architecture. Using the generated synthesized netlist, the design can be placed and routed in the actual target device. If post-synthesis simulation is desired, the synthesis tool can produce a VHDL output file that represents the synthesized results. This can be taken back to the simulation tool and resimulated. This provides a check to ensure that the synthesis did not produce any errors. Here are some more VHDL basics. The language consists of synthesis and simulation constructions. Some constructs are used for simulation only, while others can be used for both. VHDL is made up of reserved keywords like most text languages and is not case sensitive. Every VHDL statement must be terminated by a semicolon with spaces used for readability which are ignored. Comments can be added to the end of the line with a double dash preceding it, or a comment block which may be added to provide more verbose information by preceding the comments with a backslash and an asterisk and ending them with an asterisk and a backslash, similar to